Students, this is the Thermochemistry of Food Lab. And the idea is, as we study thermochemistry, we need some evidence, or it's helpful to see evidence at least, of the energy that is actually contained in chemical bonds. Our metabolism is how we extract energy from the food that we eat. So in this lab, we're going to mimic the action of a metabolism. What when your stomach and intestines do is they break down the bonds in food. Now, we can do that same breaking down process by burning. So one of the fun things that you get to do in chemistry is burn substances. Today, we're going to choose 3 food types. We've got walnuts, marshmallows, and bugles. Bugles are these chips that you can eat. They're particularly oily content, which is helpful when burning. So that's why we chose those. And what we're going to do is put some water in a test tube. And as we burn these food items, we're going to hold the burning food under the test tube so that the water in the test tube heats up. And we're going to use a thermometer to measure the change in temperature, do a little calculating, and figure out just how many calories of energy were in each of the foods as we burn them. So in the procedure, the first thing we need to do is measure out 10 milliliters of water. So I'm going to use a grad cylinder and some just plain tap water. We don't need deionized water for this lab. So I've got 10 milliliters of water that I'm going to pour into my test tube. And I've got a thermometer that I'm going to place in that test tube. And we'll get a reading. We'll give it a minute to equilibrate. A reading of the initial temperature of the water. Meanwhile, I'm going to take a piece of foil wrapped around some wire gauze to catch any burning pieces of food. And in fact, I'm going to lower this just a little bit so that it can catch all the food particles a little more readily. Next, in the procedure, we do need to get the mass of our food samples. So I'm going to use my electronic scale. And let's start with the bugles. I'm going to place the bugles on the scale. And we want pieces of food that are roughly in the ballpark of a gram. So one single bugle will do the trick. That one single bugle has a mass of 0.96 grams. So I'm going to record in my data table, the third line down, the mass of the food sample, food type 1 bugles, is 0.96 grams. So we'll set that aside. That's the piece we'll burn. Next, let's see. Let's take some marshmallows. And I want an amount of marshmallows that is in the ballpark of a gram. Let's do one single mini marshmallow. So one single mini marshmallow, I'm calling that food type 2. So in the data table, under food type 2, the blank, you should fill in marshmallow. And I get 0.57 grams for a single mini marshmallow. The third food type, walnut. I'm going to take one decent sized walnut, and I get a pretty big one here. I'm going to take a smaller piece. Here we go. This piece of walnut weighs 0.70 grams. So in the data table where it says food type 3, mark walnut and 0.70 grams. Okay, so these are the 3 pieces of food that we're going to burn. I'll set the scale aside. I'm going to use a kitchen torch to burn and some tongs to hold the burning food sample. Now, as we burn, we're going to leave the thermometer in the test tube. As long as the water in the test tube does not approach boiling, which for water at atmospheric pressure is 100 degrees Celsius, you don't need to change the water in the test tube. You can just leave it there. But if we do approach boiling, we'll have to pour out the water that was there and then add a new 10 milliliters of water. I don't anticipate that being a problem. The initial water temperature for food type 1 is 19.5 degrees Celsius. So in the data table, I'm going to mark 19.5 degrees Celsius. And before we actually ignite, I'm going to put my goggles on for safety. And let's do the bugles first. So I'm gonna hold the bugle with my kitchen tongs or my tongs here. And what's going to be important is I'll light it on fire. And once it's ignited, I'll move it over to the test tube. And as long as it's lit, I'm going to keep it under that test tube. Now, the tricky thing and a common source of error for this lab is if a student were to use the kitchen torch directly under the test tube, then you're capturing the chemical potential energy of the butane in the kitchen torch rather than the chemical potential energy of the bugles. And so what we're trying to do is capture just the chemical potential energy of the bugle as it's burning. And by tilting it so that the flame captures more of the bugle, we're in better shape than otherwise. Doing quite well here. And the reason you'll see why the foil is down below here, students, the burnt up food needs to go somewhere. And the place that is safe to catch it is a piece of foil so that you don't dirty up your tabletop. We just about have it. The flame's almost out. And what that flame is doing is capturing every last bit of chemical potential energy. I'm going to attempt to ignite it one last time. Yeah, there we go. Got a reignition here. And I'll try it one more time here. Just make sure we've got everything burned as best we can. Okay, so our bugle is now completely burned up. And our temperature is 50.3 degrees Celsius. 50.3 degrees Celsius. That's a good one. Good sample. A lot of energy in that. So if our final temp for food type 1 was 50.3 degrees Celsius, and we're going to very quickly move on to food type 2, I'm just going to transfer that same temperature in the data table to the initial water temp for food type 2. So 50.3 is the initial temp now for the marshmallow, which I'm about to ignite. Once I get it ignited, I'm going to move it over to the water. And it's helpful to kind of hold it upside down so that you get the flame kind of hitting as much of that food sample as possible. Get a little here. So I'm attempting to reignite it as many times as I can until I'm still getting some burn action here. Once it is completely burned up and won't reignite, then you know you've burned everything up. So I think we're at that point now. So I'll put the burned up marshmallow on the foil. It's a little sticky, of course. Burned up marshmallow. Smells like a campfire in here. This is one of our fun labs that it's fun not to miss, but I understand things happen. Okay, there we go. Now we'll record our final temperature after the water, or the marshmallow rather. And I got 52.5 degrees Celsius. 52.5. And since we'll move quickly on to the third food type, the walnut, in the data table, I'm going to record 52.5 degrees Celsius as the initial water temp for that food as well. Okay, we'll ignite our walnut. And again, the point here is ignite and then move the burning food sample under the test tube. And if it flames out, reignite and move the burning food sample under the test tube as many times as you can. And walnuts are generally really good at raising the temperature of the water here. Oh, this is wonderful. Look at this flame, students. It keeps going and going and going. Okay. Notice the char at the bottom of the test tube. Sometimes these test tubes need a thorough cleaning after this lab. Oh, great burning. What I've learned from experience that the more oil content in the food, the steadier it burns. So the bugles did a great job. The marshmallows did not do such a great job because there's very little fat in a marshmallow, but there's a lot of carbs. But walnuts, a lot of fat content again. So we're doing great here. And by the way, the thermometer is creeping up. We're creeping up. We're reaching, we're in the 80s degrees Celsius. Okay. Flame's still going. And sometimes it's helpful to actually stir the water with the thermometer just to circulate, because otherwise you'd have a real hot patch of water at the bottom and a cooler patch at the top of the test tube. So stirring it helps to circulate the water. You get an even water temp. Okay, great burning. We are in the 90s of degrees Celsius. It's going to ignite one more time. See if we can get all the energy that was in the walnut transferred to the water. Doing good here. Okay. And we're just about out. There we go. Okay. So the walnut is completely burned, and we ended with 94.0 degrees Celsius. Nice burn on that one. And with that data, now we'll set aside our equipment and we'll go to the board and do some calculating. So you'll need your calculator, and I'll see you at the board. Okay, students, now let's do some board work where we're going to take the data that we had collected while burning the food samples and try to make sense of it. First of all, in the data table, the numbers that we did collect already were masses of the food samples as shown here, the initial temperature and the final temperature. Let's subtract final temp minus initial temp for each food type in order to arrive at the change in temperature. In the case of the bugles, subtracting 50.3 minus 19.5 gives us 30.8. For the marshmallows, subtracting 52.5 minus 50.3 gives us 2.2. A really small temperature change, by the way. That'll be important. And then for the walnuts, a difference of 94 degrees Celsius minus 52.5 gives us a temperature change of 41.5. Other data that we need to collect prior to doing any calculating includes actually looking at the nutrition labels. So here's my bag of bugles, and on that bag, it lists in nice bold text here the number of nutritional calories in a serving, 150. They also will list in a standard nutrition facts label the number of grams in a serving. Those two pieces of data we need to record from each of these food labels. So for bugles, it was 150 calories. for every 30 grams. For the bag of marshmallows, I saved an empty bag here. It is 90 calories. And above that, a standard size serving for marshmallows is 30 grams. And then lastly, for the walnuts, 180 calories, and it is a 28-gram serving size. Okay, so we've got our data collected. Now let's run through the analysis questions for each food type. These are the 5 analysis questions, and we want you to calculate for each of the 3 food types. So I just made a table out of that. So question 1 says, calculate the number of calories liberated. For each food type, what you're going to do is take the change in temperature and multiply by the number of grams of water that we were heating up. If you remember the procedure, we were to measure out 10 milliliters of water into that big test tube. And if we know that water's density is precisely 1 gram per milliliter, then we've got 10 grams of water when we measure out 10 milliliters of water. So we're simply going to take the temperature change times 10. The bugle temperature change was 30.8. We'll times that by 10 grams of water. And that gives us 308 calories liberated. For the marshmallows, the temperature change was quite small, 2.2 degrees Celsius times 10 gives us 22 calories. And then for the walnuts, we had the most, 41.5 degrees Celsius times 10 grams gives us 415 calories liberated. Question 2 asks you to consider the number of grams in each of your samples. So now we're going to refer back to the sample sizes. So that one bugle that we burned had a mass of 0.96. The one marshmallow that we burned had a mass of 0.57 grams. And the one walnut that we burned had a mass of 0.70 grams. So to calculate this, we're simply going to take the number of calories that you had calculated in part 1 and divide it by the sample size in grams for each of the 3 food substances. So for the bugles, that works out to be 320.8. Actually, I'm going to round that to a whole number. Let's call it 321 calories per gram. For the marsh, 22 calories. And we had a 0.57 gram sample. That works out to be 38.6 calories per gram. So why don't I round that to a whole number? Let's make that 39. So we got a much lower number of calories per gram for marshmallows than bugles based on our results. In the case of walnuts, we'll take 415 calories divided by 0.7 grams. And that works out to be, this one's the biggest, 593 calories per gram. 593. So by far, walnuts, based on our data, is the most nutritionally dense or energy dense of the foods. Analysis question 3 asks us to convert from calories in a physics or thermochemistry perspective to a nutritional calorie perspective. This is where it gets really interesting. A nutritional calorie, one of the calories listed on a food label, is actually 1,000 regular calories, or 1,000 calories in physics or chemistry. So I'm going to take the 321 in the case of the bugles and get 0.321. So quite a bit smaller. Kilocalories, kcals, is how I'm going to abbreviate that per gram. which is the same as a nutritional calorie per gram. In the case of marshmallows, 39 over 1,000, that's 0.039 kilocalories per gram. And in the case of walnuts, 593 over 1,000 is 0.593 kilocalories per gram. Question 4. Now we're asked to look at the food labels, use that data that we had collected. We're going to take the number of nutritional calories divided by the serving size in grams for each of the 3 food items. So Bugles was 150 and 30, Marsh 190 and 30, and walnuts was 180 and 28. The numbers are easy to work with here. 150 over 30 is 5. Now, a nutritional calorie is a kilocalorie. So our units for the answer to question 4 is the same as the answer to question 3. So kilocalories per gram. In the case of marshmallows, it was 90 and 30. That gives us 3 kilocalories per gram. And in the case of walnuts, it was 180 over 28, which works out to be 6.4 kilocalories per gram. All right, students. Now, theoretically, your answer to question 4 and your answer to question 3 should be ballpark close. Now, I'm going to have to say, based on percentage difference, we're looking at significant differences. 0.321 as compared to 5, I'd say not particularly close. 0.039 as compared to 3. Again, I'm going to give that a not close rating. I'd say that's, it's multiples of difference. And lastly, for the walnuts, at least we're getting, something comparable. 0.6 roughly to 6 is a 10 times difference. It's better than being like a more than 10 times difference. But again, I'm going to say not particularly close. Why? And that gets us to question 6, a discussion of sources of error. Students, in this lab, we were simply burning food with a kitchen torch in an open air environment, okay, not a closed system, and holding whatever burning food we could underneath a test tube, hoping that that would warm up the water in the test tube. And it did successfully warm up the water, but think of all the energy that's lost to the air, to warming up the glass of the test tube, right? We didn't attempt to account for that in our calculations, the temperature of the test tube itself. Probably the biggest source of error is that even though I tried my best to burn those food particles, I did not get a complete combustion. So when a FDA approves the label for a food type, you have to do a combustion reaction in a very tightly controlled lab, and their equipment is much more precise. They have enclosed environments. They're not just lighting something on fire and moving it under a test tube. It's a way more precise. You could say lack of precision. You could say incomplete combustion. They can turn their furnaces all the way up to thousands of degrees Celsius. I don't think we had achieved that temperature throughout the entire food particle. Like if I were to take that burnt up bugle and crack it open, I'll bet you could burn a little more of the bugle. And so there was incomplete combustion, which explains why our numbers are significantly lower than the nutritional label numbers. If it were, something else, or like you burn too much or something, then you would expect our numbers to be higher than the nutrition label numbers. But that's not the case. Thanks for your good work.